2 years ago. So since then, we have been in touch and are currently also finalizing a joint white paper on this topic. So I'm very happy that you accepted the invitation, and I very much look forward to your talk.
Okay, thank you very much, both of you, for the kind introduction and for the invitation. And yeah, let's try to share the screen. No, not going. So, okay, I hope everyone sees the screen, full screen. Yeah, the title was Introduced Towards Auditable AI System, and this work is joint work together with my colleagues Christian Berghoff and Matthias Neu, also from the Federal Office for Information Security. So Mr. Zamek already talked a little bit about the BSI. I will give you the general introduction to the BSI. So the BSI, as a federal cybersecurity authority, shapes information security and digitalization through prevention, detection, and reaction for government, business, and society. So we're basically there for everyone in Germany for the issue of cybersecurity. And so the question is now, what are the responsibilities of the BSI in the context of AI? So first of all, the first responsibility is to take care of the vulnerabilities of AI systems. And that means the evaluation of existing and the development of new evaluation and protection methods. And then subsequently, the development of technical guidelines and standards. As a second main point, AI can be used as a tool to defend IT systems. And there the BSI can give recommendations of existing and the development of new technologies and the guideline for deployment and operation. And as a third point, AI may be used as a tool to attack IT systems. And the question from the BSI side is, how can one protect IT systems from qualitatively new AI-based attacks? And for that, of course, the BSI has to be keep track of state-of-the-art attacks and also try to build attacks to see what is necessary to be done. Okay, and today we will focus on this first point, the vulnerabilities of AI systems. Okay, the life cycle of connectionist AI systems. So AI systems, first of all, they are connected and embedded in safety and security critical applications. And these applications may be, for instance, autonomous driving. This may be medical applications. And these may be, for example, biometrics for access control, for example, border control systems, or in companies, access to buildings. And artificial intelligence systems are usually not employed just by themselves, but they're, as I said, part of a bigger system. And we differentiate here between three different modules. These are classical IT systems or CIT systems. These are SAI system or symbolic AI systems, and then connectionist AI systems. And these connectionist AI systems is what I will focus on today. And these systems are in some kind of a network and they interact with the environment. So for example, they will lead to some actuation or some decision, which will again influence the environment, and this environment will again influence the input of these systems. A classical example is, of course, autonomous driving, where you have a constant updating sensor input stream and constant update of the actuators. Okay. So connectionist AI systems differ qualitatively from symbolic AI and also from classical AI. So in symbolic AI, we have a developer that is directly responsible for designing, testing, tuning, and also it's also possible for the developer, at least in principle, to interpret the symbolic AI systems. Of course, there are really huge symbolic AI systems where this is not possible practically anymore, but in principle, it's possible. Whereas for connectionist AI systems, this is not possible in principle anymore because the developer is somehow far away from the system that will be put into operation. For the development process, the developer can only set the boundary conditions. Development cycle or life cycle, a labeled data set for in case of supervised learning is needed for training and testing. And this data set is then used, partly post-processed, sometimes used directly, and fed into an untrained network as inputs. The output is evaluated and a machine learning algorithm is used to update the network parameters based on certain criteria and optimization goals. And then after a while, when this has run for some time, you will get some output which, with which the developer is satisfied, and then it can be put into operation. The problem then is, due to this machine learning process, we have a lot of parameters. So current AI systems often have 100 million parameters or more. Like these speech processing networks sometimes have even many more parameters. So it's almost impossible to interpret what's going on in this network just without using new tools to do so. So and this poses now several problems. And these problems are, first, that the input and the state spaces of these networks, especially for image processing tasks, where these AI systems are often used, are huge. Then we have these black box properties, as I just elaborated on. And then we have the dependency on the training data. So the system basically learns what you feed the system as the training data. And if there's a problem with the training data, you will most likely have a problem in the operating system, operating AI system later on. So this leads to the conclusion that the whole process chain or life cycle has to be considered when you want to make sure that the system is safe and secure. Okay. So then one has to note, of course, as I mentioned before, these systems are embedded. You cannot just look at an AI system by itself. So I now depicted here this Connectionist AI lifecycle in this diagram. And this usually is embedded in larger life cycles. For example, you can take the viewpoint of the functional safety life cycle, where, for example, a focus is put on the concept and scope, hazard, and risk analysis prior to putting such a system into operation. And from the safety requirements, you derive and allocate then the system. And this might at this stage already lead to the conclusion, in the extreme case, that you need to exclude technologies such as AI. For example, if you ask the car manufacturers, usually AI systems are not used at the moment for actuation purposes. So they are mostly restricted to sensor processing tasks, because they say, okay, we cannot verify the system, so it's too safety critical, we won't use AI systems. This might change in the future, but this is how it looks right now. And then, of course, we have the AI system embedded into this, but not only this AI system, but also other components of the big system. This has to be kept in mind. Okay. And then if we look, then the question is asked, of course, from the BSI side, our main concern is the IT security of systems. So this has the aspects of confidentiality, availability, and data and model integrity. But if you look at it, these AI systems, it's not sufficient to just look at the IT security specific issues, but we have to consider many more aspects. And among these aspects that are important for us are the aspects of interpretability, evaluability, and verifiability. Then, of course, aspects such as performance aspects, where we have several sub-aspects such as the correctness, the accuracy, the robustness. I will talk about this later in more detail, about the error handling and the reliability, and then other aspects such as speed and resource requirements. Then, of course, aspects such as documentation, logging, and traceability are important. Now with the red border, I'm drawing the border about what is important for today's talk. Of course, the other things are important as well. We as the BSI say we don't take care of ethics or user acceptance criteria or data protection by itself. but we have to connect this. For these use cases I just mentioned, of course, the safety aspect is really important and has to be taken into consideration. Okay, so why are and where are CAI systems vulnerable? And we published a review paper on this. I will post a link at the end of the talk where you will find all the references linked. So this is this review paper from Frontiers in Big Data. And basically, we looked at the literature and tried to find out what kind of vulnerabilities exist in these systems. And I will talk about a selection of these vulnerabilities now. Now this AI lifecycle is depicted in a slightly different way, but very similar to the first one. So we have the developer here on the left side that sets boundary conditions and initiates the training. And then what is different here is we have multiple instances of this machine learning process. And the point is that due to the cost of obtaining high quality data and the cost of training big neural networks, often data as well as pre-trained models are obtained from external sources. That means that there are multiple training epochs basically done by separate people, developers in separate locations with different data maybe. And this, of course, introduces new problems. I will come to that in a bit. And once this system has put out or has resulted in a good high quality neural network or AI system, it may be put into operation. And then, of course, we have an input going in, output going out. So we can divide this whole thing into the phases: planning, data, training, evaluation, and operation. So what kind of vulnerabilities do we have? We have the classical vulnerabilities, such as the social attack on the developer, of course. We have the classical hardware level attacks or operating system level attacks, as with classical IT systems. But we have several qualitatively new vulnerabilities. I will tell you about two here. This is first is a backdooring attack. And the problem here is that, as I mentioned before, the systems are highly dependent on the training data. So if you introduce wrong training data or wrong label training data, this can result in the wrong output. And if the attacker does this in a smart way, he can only, I will show you in a bit, can do this in a very specific way. And the other qualitatively new attack I will talk about is the adversarial attack, which does not need to interfere with the training process, but it can, attacker can design an attack and directly feed it into the operating AI system. And then there are multiple other qualitatively new attacks, such as model stealing attacks, data extraction attacks, and so on, but I won't talk about them today. Okay, then we have the AI-specific attack I will use the use case of autonomous driving. Here's a road sign classification system. And the first specific attack is a poisoning backdoor attack. And in this attack, if we again use this life cycle, here we have a concrete example of traffic signs with their labels. So for example, this is the yield sign, this is the speed limit 100 sign, and so on. And if we train this, we get in operation, if this works well, in operation, we will get the correct output for the inputs, the respective inputs. For example, the speed limit sign 100 will put out a speed limit 100 decision, the same for stop sign. But now if an attacker comes and inserts a malicious data set, for example, he uses a stop sign with a post-it on top, but assigns a different label, namely the speed limit 100 label, then everything else later on in operation will work fine. But for the specific trigger, backdoor trigger, we will get the wrong output. Okay, we did this in the lab. I won't go into detail, but it's easy to reconstruct this in the lab. And you will see, for example, here for this post-it example, or for another example where we use 4 different stickers outside of the traffic sign, you get with even a very low percentage of poisoned data, you get high qualitative and successful attacks. The second example, AI-specific attack I will talk about, is an adversarial attack. And in the adversarial attack, we start from the normal operating condition of such a AI system. So for example, for the stop sign, the AI system processes the input and puts out the stop as a decision. But now an attacker can modify this input, for example, by adding some random noise, not random, but specific noise to the input. Or you can use like stickers. I will show this later. And this input, modified input, will use or will exploit properties of this connectionist AI system that will then lead to the wrong classification. And for the attacker, for a targeted classification, for example, he can target the system to output a speed limit 100 instead of the stop sign. And now if you imagine there's only this one system for traffic sign classification, this could lead to serious safety issues in autonomous driving. Okay, so now the problem is you say, okay, it's difficult for the attacker to design the system if he does not have access to the real system here, so no white box access. So this would be the first line of defense, to not allow the attacker to access the real system. But the problem is we have the transferability issue, property of these neural networks, and this will allow the attacker to use substitute models to efficiently design his attacks. Yeah, so he can have an optimization procedure on the substitute model, design the attacks, and test them on the real system. Yeah, to have some examples. So this is very simple, simple examples from a student. So this is far from perfect. So we at the BSI are not a research institution per se, but we try to somehow redo these attacks for this traffic sign classification task. And we used a patch approach. So we let the system optimize a certain patch size and say, okay, if you add this patch to the image, we want to have a specific output. And in this case, with the stop sign and with these two direction signs, we trick the traffic sign classification system each time into outputting a speed limit 30 sign. Okay, what kind of measures of defense are there? So there's a huge body of literature on possible defenses against attacks on AI systems. So we have, I show you the picture from before again. In red, we have the attacks. In blue, I show different defense methods. So of course, we have the classical IT-based or classical IT defense methods. This is, for example, attack prevention, good training of the developer regarding AI-specific risks. Then we have things like attack prevention by feature squeezing, compression, randomness. So we do a pre-processing of the data, but this is only successful to some extent. Then we could have the idea of multiple systems that run in parallel with a majority vote at the end. Then there is what is really right now considered the most efficient defense line is the attack. It's an adversarial training, where during training you will already feed the system with malicious example, but which are correctly labeled as malicious. So the system learns these examples, but for that you need to really have a representative data set of malicious examples. This is a difficult task by itself. Okay, and then there are, of course, other methods like the certification of training data and the training process, the supply chain, the evaluation process, and the final decision logic. And of course, things like standardization. Yeah, so basically there are a whole lot of possible ways to defend the system, but as practice shows, none of these methods is sufficient by itself. So they can all be circumvented by adaptive attackers. So basically the message is single measures are not effective against adaptive attackers. And somehow we have to consider a combination of these defense methods and even improve on some of these defense methods. Okay, now I was talking about malicious examples and attackers, but there's also the problem of robustness of the system, this robustness aspect that I mentioned before. And there we did a little project with the ETH Zurich, or the spin of Latticeflow. You will find the report later on in the literature and also under this link. And the idea is to test and to improve the robustness of neural networks. And for this, we have a test data set, and we test the robustness, derive a robustness score of the system, and then derive failure modes from this. And with these failure modes, we can elicit the properties and, for example, improve on our tests. And in the end, we can improve the data set. And with the improved data set, we improve the robustness of the whole system. I will give you some more specific examples here. So for example, first one looks, of course, at basic properties like geometric perturbations, like scaling, rotation, translation, at color perturbations. And then, of course, one can look what is a more natural example, of course, I will give you an example in a bit. It's a combination of properties. And then still these perturbations are too simple. Here you see some exemplary robustness scores on the right side. But of course, this is not sufficient, because in real life, for example, consider the example where you have a tree with a lot of leaves and the sunlight shining through the leaves on top of the traffic sign. So you have a little bit of wind, then you have fluctuation of bright and dark spots on this traffic sign. So what we did in addition, we looked at adaptive brightness, robustness, and then we looked also at natural examples like task-specific properties like stickers on the road signs. And the idea is then to really in the analysis see where the system fails and if this failure is systematic and how it can be improved on. Okay, to give you more examples, for example, for these natural occurring stickers, this is a big problem because you have these stickers, if you look at this in real life on a lot of signs, and with these stickers on the signs, you get a big decrease in robustness. So if we looked at the robustness with two different trained networks, and for both the robustness score was decreased by a lot when using the sticker approach. And if you look in general at these traffic signs, you will see there's a lot of natural perturbations going on that will pose a big problem for these systems. And as I said before, a combination of multiple perturbations is rather in real life the normal case and not the exception. So we looked at, for starters, we looked at the combination of two perturbations. In this example, in this plot, the robustness score is shown for the combination of translation and scaling perturbations. And if you combine both of them, the robustness score drops to 85.5% compared to 93 and 94% for translation and scaling alone. And you see here the distribution. Okay, most have the same robustness for most of these combinations, but some of the combinations of translation and scaling will show a highly decreased robustness performance. And then we also looked at the order of combination of these perturbations. For example, for scaling and blurring, if you first do scaling, then blurring, you will get a different robustness score than doing it the other way around. So there's still, this is just to show that there's a lot of work to do when considering robustness. In reality, we have the combination of a lot of perturbations that have to be considered, and this is a huge parameter space. Okay. Then I will come to the formulation of requirements to give you a short introduction into this, not going into detail. So the point is that the development of an AI system is an iterative and complex process, which may be divided into phases. And usually this process, as I mentioned before, is highly non-linear. So the developer will do everything to derive or to have a functional, good performing AI system in the shortest amount of time. So basically, he does everything to speed this up and uses his own experience, what kind of parameters need to be changed, what is the best data to use, and so on. So there's a big back and forth between these phases: planning, data, training, evaluation, and operation. But of course, for analyzing this and for auditing these systems, this poses a problem. So this is why we take a linear view on this. Of course, by these arrows, we indicate this is, of course, always a feedback system. And now you can look at these different phases and look at different aspects of these phases. So for example, for the planning phase, you could look at the problem statement, at already available solutions, at the personnel, at the data set, at the AI model that is going to be used, at the learning method, at the feature selection, at the runtime system, and so on. And you could formulate requirements for this. First, on general terms, you can do this for all of these phases. And the point is you do not only do this usually for the functionality aspect, but also for aspects such as reliability, at IT security, at acceptance criteria, at criteria of data safety, documentation, and so on. So you extend it, and it depends on the use case, what kind of aspects you need to look at. So you would basically formulate generalized requirements. And now the question is, if you go from this general model to a specific model, like for example, for the traffic sign classification, what changes? And we looked at this. I won't show you the details because, yeah, basically this is big tables with a lot of questions for the requirements. But the output is that the generalized AI lifecycle model is compatible with and helpful for the specific road sign recognition system. So we identified 3 different cases. So first, where domain knowledge is required, the generalized model has to be concretized. So for example, one of course has to know under what kind of conditions the system is used, what kind of signs may appear due to law, what is the practical experience of people working on the roads and deploying the road signs, and so on. Then in other cases, if-else decisions are sufficient. For example, do we need a supervised learning method or a non-supervised learning method? And there are a lot of these if-else decisions. And then the third case, in many requirements, the requirements may be directly transferred from the generalized model. So as of now, no substantial revision or extension of the generalized model is needed from our point of view. But of course, we have to use, and this is our future thing to do, is look at multiple use cases that we have to examine and to compare to verify that this generalized model holds also for these use cases. And in the end, the idea would be also to have some kind of a modular toolbox that you can use where you can quickly adapt this generalized model to all kinds of use cases. Okay, now we come to the open challenges. The open question in the context of auditability, IT security, safety, and different aspects. So I try to depict this in this figure, which will also be published soon in this white paper that Mr. Samek just mentioned. It will probably come out this month. So if you're interested, visit the website I link at the end, or the Fraunhofer HHI website. We will publish the white paper there soon, and then we will have many more details on these different aspects. Yeah. Okay, so coming back to this figure, we have depicted here in this light gray, we have a whole system life cycle. So, and part of this whole system life cycle, as I mentioned in the beginning of the talk, we have this, for example, this Connectionist AI life cycle. So from planning, data, training, evaluation, operation. And there are different aspects that are important for task and environment of this Connectionist AI lifecycle system. These are the aspects: IT security, robustness, safety, trustworthiness, cost, risk, performance, and so on and so forth. And then, of course, there's a question: are there any formal definitions, metrics, and priors available concerning the task, the environment, and these different aspects? And depending on this, if we now look at the different players and the different components of this life cycle, we see that there are many open questions. For example, when looking at the developer and the user, the question is how much communication do you need between developer and user? How much information transfer so the user is informed which kind of boundary conditions the system works as expected, where he might expect some failures, and so on. So basically for this, we need more education and training. Then, of course, there's a question of the acceptability of uncertainty and failure probabilities. So the point is, up to now, only for very few limited cases and boundary conditions, it's possible to verify these Connectionist AI systems. So in the most use cases, basically what you have to cope with is that there's uncertainty and there's a certain failure probability. And this is what I mentioned in the beginning. For example, the automotive industry, what you don't see at the moment is AI systems in the actuation systems, exactly due to this problem, because there's no acceptance of uncertainty and failure probabilities right now. Okay, this holds not only for the CAI lifecycle, but also for the whole system lifecycle. Then we have the component data. First, the task space size versus verifiability. This is what I just mentioned. The larger the task space is, the more difficult it will become to verify the system, because the parameter space gets larger and the things you need to evaluate get much larger, and it's almost impossible for real-life tasks. Then for the data, there's this IID assumption. So the identical and independent distributed data. If you don't have that, what is the normal case, then you will get problems in the data. And the question is, will this cause big problems, or is this acceptable? From the machine learning standpoint, we have, of course, the issue of plasticity versus stability. For the Connectionist AI model itself, we have the problem of complexity versus interpretability. So there's Mr. Samek is the expert. I guess he will ask some questions concerning this later on. And then we have things like online learning. What politicians often talk about is the online learning aspects of AI systems. Up to now, I don't, and my colleagues, we don't know of too many systems that really employ online learning, but of course that they are frequently updated, such as in the Tesla cars. So the question is, what is the drift versus update and test frequency? And then there are other things like generalizability versus scalability, integrity and quality assurance across the supply chain, the white box access versus intellectual property. So as I said, it's of course easier to audit a system if you have full access to data, to documentation, how the development process happened and so on. But sometimes it's not possible due to intellectual property rights. Then you have the cost of high quality attacks versus high quality defense. So yeah, so these are a lot of issues that are still open. Okay, so if we take this zoom out view, how to achieve acceptable levels of IT security, safety, audit quality, robustness, and verifiability. So we have these multiple trade-offs. On the one hand, we have the complexity shown on this axis here. Complexity, task space size, uncertainty, generalizability, and so on. And on this other axis, we have IT security, safety, robustness, stability, auditability, and so on. And the point is now that the lower these aspects are, like complexity, task space, and so on, the easier it is to achieve secure and safe systems, robust systems, and so on. And the larger, for example, the task space and the complexity gets, the more difficult this gets. So one point to improve the safety and security is to create favorable boundary conditions. So to make the smallest possible complexity, the smallest possible task space size, and so on. On the other hand, we have, of course, research and development. And with advances in technology, we can, of course, raise this. So with higher complexity, we can keep the same level of IT security. Yeah, so we have to basically, at the moment, work with both of these parameters. Advances in technology, try to advance this as much as possible, but at the same time, this is not sufficient. We need to really look at these boundary conditions. Okay, then for further reading and further information, there are some BSI AI related documents. So there's a whole more literature, but I will just link at the BSI literature for now. So there you will find more references. So we have a website. At the moment, it's only in German, but it links some English, or most documents are also available in English. So this is at www.bsi.bund.de/ki. So KI for künstliche Intelligenz, which is a translation in German for artificial intelligence. So, for example, we have a paper put out on secure, robust, and transparent application of AI problems. We have our colleagues in another department. They just published an AI cloud service compliance criteria catalog, which provides AI-specific criteria which enable an evaluation of the security of an AI service across its life cycle. At the moment, only to some basic extent, but it's a start. Then we have published this review paper that I just mentioned before. We published this paper with the ETH, this report with the ETH Zurich, which I talked about, the robustness assessment. And then soon, as Mr. Zamek mentioned, and I just mentioned, we will have this white paper towards auditable AI system, which will appear hopefully sometime this month and will also be linked on this page. Okay, then last slide, basically. BSI is involved in several national and international cooperations and standardizations efforts. For example, on the national level, we have a working group with the Association of Technical Inspection Agencies, the VDTÜV. So we have a group with a focus on mobility, and we have the goal to develop evaluation scenarios for selected use cases until the end of this year. Then we have an administrative agreement with the Kraftfahrtbundesamt, the KBA, that is the Federal Motor Transport Authority in Germany, in the context of vehicle type approval and cybersecurity. Of course, later on, so our plan is also to develop a technical guideline and then feed that into international standardization there in the UNECE, for example. And then we have with the DIN DKA an artificial standardization roadmap where the BSI takes part. And then we take part in several international initiatives, for example, in the ETSI industry specification group on secure and artificial intelligence, or on the ENISA ad hoc working group on AI. Yeah, with that, I want to close. Thank you very much for your attention, and I'm looking very much forward to your questions and comments.
Yeah, thank you very much. It was a very, very good, inspiring talk. Do we have questions from the audience? So maybe I can start with one. What do you think? I mean, can we embed an unsecure system in a secure environment to make it secure? In other words, I mean, like, for example, if you go to the moon, to space, things often also have some failure probability, but due to redundancy or like other designs, you are kind of still able to reach appropriate system robustness. So can we do a similar approach to machine learning models and the AI technology in general?
Yeah, I think so. This is this functional safety approach, I think, where we can say, okay, we look at the whole system and we need to make sure that under certain conditions, we have a certain probability, or we are below a certain probability of failure. And this can be achieved, of course, by different measures. As I mentioned before, for example, we could have redundant systems. We could have multiple AI systems, or we could have another classical IT system, which will check that the boundary conditions are within the scope where the AI system is specified for. So I think it really depends on the requirements, on the use case, and on the boundary conditions. But I think in many cases this will be possible, and it's already been used. For example, in the automotive and the autonomous cars, driving assistance systems, you already have this AI systems. They have an impact on security, but of course, up to now, there's a human in the loop. And then in the future, the question is, are they secure and safe enough, or do we need backup systems there, or redundant systems? And another remark, the automotive industry often claimed, okay, it's no problem because we are redundant. So for example, for the traffic signs, we have a map with all the traffic signs on this map. And if the wrong traffic sign is, the traffic sign is wrongly classified, we will see there's a discrepancy with the map data. But this is not always true because, for example, the GPS system may fail and you don't have your position. Then you need to rely on this. And this has been shown for many of these systems. So you have to be careful at least.
Mm-hmm. Okay, so we have some questions from the audience. So first one, like, how long do you think it will take until there are clear criteria for audible AI systems? And then do you expect changes in the regulatory landscape, or are the rules which we have sufficient?
No, I think no. So I think there are two different approaches, but one is not going to work out. So one is to say, okay, AI systems are completely new. We need to make complete new rules for the AI systems. I think this will not, it will not work like this. So basically we have to build up on the existing regulations and standards. Oh, I have to start the video, sorry. We have to rely on existing standards and regulations and build up on this for the AI specific aspects alone, because the systems are always embedded. There's not just the AI system, it's always embedded in a larger system. And there, of course, we need to make a lot of progress still. But I think the sequence is like this. We will start for specific use cases, which are rather simple to handle. And this is already the case. There's a lot of initiatives that look at specific use cases, and then we will have specific standards for these use cases. And at the end, when we have a lot of these use cases and the knowledge we derived from this working with these use cases, we will have a more generalized model. So I think it's a continuous process. So first requirements and first standards are already appearing, but it's still a very vivid and changing subject, yeah.
Mm-hmm. And about the quality metrics, I mean, you talked about the robustness score. Do we have this kind of like metrics to measure and quantify robustness of a system, or do we have kind of scores and criteria which are sufficient for measuring the trustworthiness of an AI model or AI system?
Yeah, so I think this really depends on the context again, what is sufficient and what is not sufficient. There are a lot of metrics, but not all of these metrics are sufficient yet. For example, one problem is if you only optimize with the metric for the performance of the system, and then later on post hoc, you will then optimize, for example, for the robustness against a certain type of attacks, usually then your initial performance will decrease. So what you then need in that case is to have a co-optimization with both goals and metrics. And this, I think this will be a big issue for the future of how to optimize for all different kinds of aspects. Because as I've shown, this is a complex thing with a lot of different aspects and viewpoints. And in the end, we need to satisfy a lot of these conditions at the same time, at least for some use cases. I think this will be the biggest challenge.
So I think the last time where we had the seminar, there was a question like saying that maybe we shouldn't look at the worst case scenario always, but we should try to look at the average robustness or take like the product of the probability and the costs which are assigned to failure. So what do you think about this, such an utilitarian approach?
Yeah, I think for some use cases, this makes much sense. But if, for example, the use case is safety critical, like in the health medical area or in autonomous driving, if then someone dies because of such a probability, we will have a big problem. So I think, again, this is a good thing to start with those use cases where you can do this, and then step by step improve these systems, make them more robust, get better metrics, get better defense methods, high robustness, and try to use this knowledge also for these other use cases where safety is really a big issue.
But do current systems fulfill this requirement? I mean, for example, in autonomous or in cars, are the systems all like certified in a way so that you can clearly say that nobody will die because of a failure, or do they still have some risk to? No,
it's a very good question, and I think this is a political and ethical thing to discuss. What kind of failure probability do you accept? Because of course, even if a human is driving, it's not error free. is driving mode. So the question rather is, I think, from my point of view, will these systems be better than the humans at the moment, or at least as good? I think this should be the baseline condition. You should always have this comparison with existing systems and try to be better than this. And then, of course, it's a political and ethical discussion. I think from the technical point of view, at the moment, it's not possible to really verify the systems in such a complex environment. So you have to cope with errors. And then it's a decision on another level to say, okay, we accept it or accept it not, or they will tell you, okay, this is a line you have to draw, this is a threshold, and if you're below, it's okay, if not, no. Mm-hmm. Does this answer your question?
Yes. So one question from the audience. So against the backdrop of the leaked draft of the EU regulatory framework, it seems like that high-risk AI systems will be subject to conformity assessment, either in self-assessment or a third-party assessment framework. So how close to being able to define and run conformity assessments are we?
So yeah, so as I said, this depends on the boundary conditions. As I said, for example, we have this published by the BSI, this AI cloud catalog. So, and there it tells you under which kind of conditions you can make this assessment, but this only covers basic aspects at the moment. And so you can say, okay, on a basic level, you can do this, but you cannot do it for all kind of boundary conditions and for all kind of requirements. So I think, again, this is a iterative process, and subsequential, we will get better and better in this. And we have first examples, but it's, I think in the next 2 to 3 years, we will see a lot of more of these. Mm-hmm.
And like, just out of curiosity, do you think, I mean, we should also change the models which we have? Like, can we maybe instead of regularizing like the evaluation process, we could also like have some regulatory criteria on the models we use? Maybe we need to create models which are per se either easier to audit, to validate, or which are more robust and more trustworthy.
Of course, I think this is, as I said, we need to consider all aspects of this life cycle. And this is one important aspect. Of course, the trend is going to this end-to-end learning, to have bigger and bigger networks just to feed in all the data and then get out some result. And this is very efficient from the cost perspective, because you don't necessarily need to have highly trained developers. You don't need to try different models and so on. You just will throw everything in, get a good result out from the performance point of view. But I think in the long run, this will lead to problems. So the alternative, of course, would be on the one hand to try to minimize these models, even using the same technology of these models, maybe even to use modular modules, smaller modules that are combined, and try to verify these modules. But of course, then you have the problem of the interaction of these modules. This is one aspect. And the other aspect is to use qualitatively different models. And I think that it's really important. It's also missing to some extent to have a really good overview and good analysis, which model is good for which task, and from these different points of aspects. So up till now, it's more academic, but really to look into practice. So what for this application, comparing this range of different models, which is one best suited from the aspect of cost, from security, from safety point of view, from auditability. And I think this will be a very important issue in the future, which has been neglected to some extent.
But like the companies which you are talking to and the different people who are kind of contacting you, so do you have the impression that they kind of move towards this direction, or are they simply relying on this end-to-end training because like the community is doing so, and we have like this nice frameworks to train our models, or do they actively try to make a step towards more trustworthy models?
I think the first is the case. So that at the moment, no, I think they are getting more and more aware of these problems of trustworthiness. But what I've seen so far, so we have only limited access, of course, to the real development systems. But what I've seen so far, this is still this classical way of going towards bigger networks, end-to-end learning, and so on. But in the academia, of course, there are a lot of good examples. For example, there was this Nature paper by the University of Vienna, where they showed that biologically inspired networks, for example, for car steering, which are much smaller, they are better, the interpretability gets better while preserving the same performance of these larger models. The problem is it takes time and new ideas to use them, and they're not always generally applicable to all kinds of use cases. So you really need to make custom models for the use case. At least it's not this toolbox yet, where you say, okay, I can choose from all of these models and have some guideline which model to choose for which use case. But I think this might be an option for the future. I'm not sure, but personally, I think this would be a good idea to go into this direction.
As there is a question regarding explainability, so this is also something which I wanted to ask. So is the lack of explainability a bottleneck in driving auditability for deep learning? Or in other words, do you think that we need to be able to understand and interpret the model in order to audit it? Or could we in principle also audit a black box?
So this again depends on the use case and on the boundary conditions and on the task space. Of course, if this is a safety critical system and we have a complex model, then we have no means of really testing all possible inputs for the system to make sure that there is no failure. So if we would have a good means of interpreting this model and really understanding what's going on inside, we could make the system much more secure without this problem of having to evaluate all the complete input space, which is often very huge. But of course, in other use cases where we say, okay, we can accept a certain probability of failure, then we have other means. Of course, it would be nice to have the interpretability there as well, but maybe we don't need it in every case.
Okay. So another question, like, will we have an open source system for people outside large organizations to participate in the ecosystem?
So what is meant for auditing this system, or for the what is
I think so. I think it's related to auditing. So could you imagine to have like some open source initiative to like really combine all the efforts and all the ideas around the world to make this happen?
Yeah, I think this is, so I cannot speak for everyone, also not everyone at the BSI, but I personally think this is very important because this is such a complex issue. No one company or institution can really develop all of this at once. And I think it's what is also important, not only that we can progress faster if we combine our knowledge, is also the trustworthiness that people can really see what's going on inside of these auditing systems. Because then again, you would have another black box, a company saying, okay, the system is safe. So what does it mean it is safe? So I think from my perspective, I would like to know what is going on inside and what is being tested. So I would favor this solution. But of course, you never know what happens. Then big companies have huge resources and then will keep the advantage for themselves of developing this. So this is,
So do we have other questions? So I think we have time for one more. Good. So if not, then I would really like to thank you for taking the time and giving us this inspiring talk. Thank you very much. And
yeah, you're welcome. And thank you very much again for the kind invitation and giving me the opportunity to talk to you. So if anyone out in the audience is interested in these issues, please feel free to contact us at any time. We are open for any kind of discussion and collaborations if possible.
Thank you.
Thank you, Wojciech, and a big thanks also to Arndt von Trickel. We would like to run a little poll to see how much you like the webinar, and so my colleague will put that on the screen. And in the meantime, I would like to take the opportunity to highlight a few sessions that are coming up. So next Tuesday, the 20th, we have a session on on creating safe digital spaces using AI and esports. Then the Tuesday after that, on the 27th of April, we have a workshop on using satellite imagery and machine learning classification using QGIS. And then in the Trustworthy AI series, next Thursday, we have a session, again, hosted by Wojciech, on towards trustworthy AI systems. And with that, I think we've reached the end of the webinar. Thank you very much, and I hope to see you all next week.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector.